So let's talk about computing the power at the output of a linear system of some random process. If you want to think about it as the output process is a noise random process, in that noise was input to some linear system, it was filtered, and what came out was another noise process, that's fine. But really, what we're going to do here is good for any output random process. If you want to know the power of that random process, what we do here will be applicable. So for the sake of argument, again, we're going to call the output of the linear system y of t, just like we always do. And what we would like to know is, what is the power of this output random process? What is the expected value of y of t squared? Because this quantity is the expected value of its instantaneous power. Well, if you go back to our expression for ry of tau, you can see that this can be computed by evaluating the autocorrelation function of the random process y of t at just one point, namely tau equals 0. Because when tau is 0, the definition of the autocorrelation function turns into y of t times y of t, which is y of t squared. So what this says is if I'm only interested in knowing the output power, I don't need to compute the entire autocorrelation function. I only need to compute the autocorrelation function at one point, tau equals 0. So sometimes you do want to know the entire autocorrelation function. That's a normal thing to want to know. But if all you're concerned about is how much power is in this random process, you really only need to know the autocorrelation function at one value of tau. So let's think about how that simplifies the computation when we don't have to compute the entire time domain function ry of tau. We just need to compute it at one point. So if you recall the expression that we ended up with from our last series of videos, this was for a linear time-invariant system with a wide-sense stationary input. It turned out that the output autocorrelation function was related to the input autocorrelation function via a convolution. And it was convolved with this function f. F itself is really the convolution of the impulse response of the system convolved with the time-reversed impulse response of the system. We called that the function f, and that allowed us to write the autocorrelation function as the single convolution integral. So what we're interested in doing now is, if we're just concerned about output powers, we're interested in evaluating this at the single point tau equals 0. So let's go ahead and do that. Let's let tau equal 0. So that means I need to replace tau equals 0 here, and all the taus over here are replaced with 0. So there was a single tau here, tau minus u. When tau is 0, that just turns into f of minus u, so I end up with this integral. From this line to this line, what happened? Well, if you recall, think about how this is constructed. The function f is the convolution of h with its time-reversed copy. And we said that this function f, because of how it's constructed, is always an even function. So that means, by the definition of an even function, f at time minus u is the exact same value as at time f of u. So it simplifies to this line of math right here. So what that says is, if we want to know just the power of the output random process, we only need to compute this value. This value is given by this simple integral expression. All I needed to do is find out what the f function is, multiply it times the autocorrelation function of my input, and then integrate that function across all time from minus infinity to infinity. In other words, the output power is just the area under the product of these two functions. So sometimes you do want to know the entire autocorrelation function of a random process, and in that case you really need to evaluate this integral for all time tau. But if you're really only concerned with finding the expected value of its second moment, its expected value of its instantaneous power, the computation is actually much simpler. It's just a single integral that you need to do that integrates the area under this function.